Everything can is ill can come. So we changed it, and next speaker now is Jerome Romagosa.
Yes. Hi, yeah. So today I'll be talking about one of my kind of introduction topics into philosophy of quantum mechanics, unlucky branches, and then talking about some issues with disconfirmation, confirmation in many worlds. This is very much still a sketch, so the basic overview is that many worlds entails the existence of unlucky branches, parts of the universe or the multiverse in which we observe things, certain outcomes of experiments that differ substantially from the kinds of outcomes that we would expect from standard textbook quantum theory. So particularly maybe strings of upward measurements over and over and over again that don't quite align with the standard way of looking at the Bohr rule. So with that in mind, David Albert in 2015 claims that many worlds interpretation is insusceptible to ordinary confirmation and disconfirmation and can't make sense of our sense of surprise when we observe a set of low probability experimental results that would be associated with something like an unlucky branch. So when conducting these sorts of experiments, his view is that any experimental data one observes could be regarded as in some way compatible with the many worlds interpretation, since there's going to exist some branch in which precisely that outcome does occur. Here's a general outline of the talk. So first, I'll briefly go over Albert's allegations again. Then I'll outline my first thought experiment called Bohr star, provide a quick response to that in terms of David Wallace's decision theoretic strategy, and present a potential other worry that still remains. Then I present my second thought experiment, which I call Wallace star. And in order to introduce it, I do a little bit of background on perdurantism in branching worlds, talk a bit about self-locating uncertainty, and then use those to try to tackle David Albert's allegations about surprise and disconfirmation. So first, again, Albert's allegations. I have a long quote here, but the essence of it is, why should it come as a surprise whenever we observe a low probability string of results? How do we make sense of this sense of surprise? And I'm going to try to suggest that we can make sense of the surprise. My way of doing it is to appeal to perdurantism and self-locating uncertainty. And then we have this question of whether or not the many worlds interpretation is susceptible to ordinary confirmation and disconfirmation, why any set of results should cast doubt on the many worlds interpretation. And I think that this is perhaps a little bit less clear, although I do think that David Wallace provides a very good strategy for going over this. So the first thought experiment, to just kind of intuition pump you a bit about the unlucky branches, what I call Bohr star. So imagine it's the early 1900s. This isn't exactly Niels Bohr or anything, but he performs, scientist in the early 1900s, performs a study using something like a Stern-Gerlach measuring device, sets up a particle in a particular way. We would call it maybe like the z-spin eigenstate, and he wants to measure the x-spin. So every time that our friend Bohr star performs this measurement, he gets the same outcome. Why? Well, we're looking at Bohr star along a particular branch of the wave function where that's growing over time and the same measurement is occurring. So the way that I'm going to kind of use some made-up terminology here is that we can call the universal outcome distribution something like what these results would look like across the entire wave function. Then I'll call the in-branch outcome distribution something like what Bohr star observes within his particular branch. So here, the in-branch outcome distribution is just up over and over and over again. And of course, the universal distribution is something that's going to align with the Bohr rule. So there's this tension here between what Bohr star observes, and what the world is actually like. So hence, Bohr is unlucky. So some preliminary concerns with this are, first, what supports our ordinary intuition that the data that we observe reflects the universal distribution rather than merely some possibly unlucky other distribution? How do we know that basically the probabilities that we observe are the ones that are actually the way the wave function is, rather than just being in an unlucky branch? If we think that the universe is branching in some way, if we think that option is on the table, why do we think that we have direct access to the objective probabilities? So the second sort of question here is, why should we take ourselves to be lucky rather than unlucky? And then why ought we think that Born's rule yields the correct probabilities to begin with? So what justifies our faith in the Born rule? So David Wallace provides a lot of really good responses here in his 2012 book. I'm not going to go into detail here, especially because I have a pretty short presentation. But I think kind of in summary, the way I take it is Wallace provides an account for why it's rational for us, on one hand, to behave as if the squared amplitudes of wave functions are probabilities, and as if the probabilities given by the Born rule will obtain in the branch that we happen to inhabit. In turn, this justifies why, given the kind of data that we in fact observe, which confirms to the Born rule, why it's rational for us to believe that the probabilities given by the Born rule are the correct ones, and that if the universe has a branching structure, like the one we have in many worlds, that the in-branch distribution that we have observed should align with the universal one. This gives us reason to believe in the Born rule. So I'm going to skip some of this to get on to the more content about my talk, because I don't think that all of this is actually all that necessary. So the important points here from Wallace's account for me are that he says, even though there's going to be unlucky branch inhabitants who will use his strategy and sometimes come to the wrong result about what the correct theory of the world is, that's okay. Whenever we adopt a kind of rational strategy, the important point is that it works for most of those who adopt it. It's okay if it fails sometime. So the motivation here is that we could use Wallace's strategy and suppose that you are an unlucky brancher who adopts this strategy. You are going to be inclined to take it that the kinds of observations you observe are the way that the world actually is. So whenever we do a bunch of experiments, observe some results, we're going to take it that the probabilities that we observe are the objective ones. We don't tend to think that we're profoundly unlucky. But as a matter of fact, if many worlds is right, there are going to be these unlucky observers. So the second important point for my account here is that Wallace thinks we ought to reject the hypothesis that, reject low-weight hypotheses. He says that decision-theoretic representation theorems tell us that we should reject hypotheses according to which our own branch has low weight. I'm going to say a little bit later that in some respect, I think we can do this without rejecting many worlds, even if we happen to observe unlucky results. And then the third important point for me is with respect to disconfirming many worlds. So this is what I'll use to talk a bit about Albert's initial concerns. So here he says that an experimenter should reject the Everett interpretation if he detects results which occur in sufficiently low-weight branches. So this last principle for disconfirming many worlds is what I'm going to use as the pop-off for my Wallace star thought experiment. So before we get into the Wallace star thought experiment, I want to give some brief background on perdurantism and how I understand self-locating uncertainty in perdurantist terms. So generally, perdurantism in ordinary kind of three-dimensional metaphysics would say that have some object and it persists from time t1 to a later time tn if it has temporal parts instantiated at all the times between t1 and tn. So the object O is constituted by these temporal parts p1, p2, p3, and so on up until the time the object goes out of existence. And that's all fine and well in maybe temporal parts. So I have two hands. I'm using Wallace's example here. I have two hands. These are parts of my body, like spatial parts. So a temporal part would be, well, there's a temporal part of me now. There's another temporal part of me now, and so on. Good, thank you. So yes, this works out fine and well in four-dimensionalism, where we just have three spatial dimensions in time and standard single timeline. But what happens when we have something like a branching world structure in many worlds? So we can apply the perdurantist framework here and think that when the universe is branching according to many worlds, we have this, the way we usually talk about it is that maybe some object splits off into two copies. But I think there's another approach that's more intuitive for perdurantists, which is the Lewisian view that says we have two worms that share some temporal parts, but don't share other temporal parts. So for instance, looking at this diagram here, at time 1, there's only a single thing. We can call that like copy 1. And then a branching event occurs at time 2. And now we have two separate space-time, where it's two separate copies. One we could call C2A, the other C2B. The actual object, call it OA, has temporal parts C1 at time 1, and another temporal part C2A at time 2. And then that partially overlaps at time 1 with another object that has temporal parts C1 at time 1 and C2B at time 2. So the idea here is, well, if I undergo a branching event, I have a temporal part now before the branching event, and then I will be one of these two worms, and my history is going to be traced along the entire worm, and there will be one copy that is a part of me, is a temporal part of me. There's going to be another copy that's not a temporal part of me. So my history is from the time I come into existence, the time I go out of existence, but there will be things much like me that I share temporal parts with, other worms that share a past with me but not a future with me. So applying the framework here to try to talk about self-locating uncertainty, Vaidman, his 2012 paper, notes that self-locating uncertainty provides an explanation for trying to make sense of apparent probabilities in many worlds interpretation. So the way I want to talk about this is, well, I guess first I should briefly talk about the way Vaidman talks about it. So Lev says that paradigm case is before a branching event, I know exactly what's going to happen in the world. I know I'll have one copy in one branch, another copy in another branch. But if you put me to sleep before the branching event and then wake me up after the branching event, I will be uncertain as to where in the world I am, which branch I occupy, until I learn the result of the particular measurement. Here, I want to explain this in perdurantist terms by saying that this is because my temporal ancestor prior to the branching event has a plurality of subjects that it's a part of, a plurality of human agent entities that it's a part of. And at the time, before the branching event, my future is in a lot of ways uncertain to me because I'm a part of many futures. My temporal part that's instantiated before the branching event is the part of a number of worlds, other than the one that I will identify with. So after the branching event, I can say I am here, in, let's say, the branch where I observe an upward spin. But prior to the branching event, the entity that I was instantiated as in the world, this particular temporal part, is part of both me and something that's very much like me, but has a slightly different future than me. And of course, these futures diverge as the world continues to branch. So another way of phrasing this is to say that there is a fact of the matter about who a subject like me is when taking the God's eye view across all of the branches and taking a look at an entire history of a branch, but there's no unique fact at any time about which subject a temporal part belongs to, because it belongs to all of the futures, right? So for a subject S, the only temporal part that's instantiated at time ti is that part pi, and pi is not exclusively a temporal part of S, but rather a part of a plurality of subjects with unique histories in the future. And of course, for any temporal part that I have, say this one, if I were to start doing a bunch of experiments, my temporal part instantiated now will be the temporal part of both lucky subjects and unlucky subjects. So if I were to start doing, or if my temporal part now were to start doing a bunch of measurements, my temporal part now will have a future, will have successors in the future who are unlucky. So now I can take a turn to Albert's first allegation, that we can't make sense of the sense of surprise. So he says, why, for example, should it come as a surprise on a picture like this to see what we ordinarily consider a low probability string of experimental results? So my inclination here is to compare this to a lottery. So, say it's a lottery with 1 billion people. So you have 1 in 1 billion chance of winning the lottery. But we all agree that somebody will, in fact, win the lottery if all of the tickets to the lottery are bought up. Point being here, I'm not surprised to learn that somebody wins the lottery, because I know deterministically that if 1 billion tickets were bought, there's 1 billion tickets to the lottery, one person is going to win the lottery, even if that seems very unlikely. Now, I would be surprised to find out that I am the one who wins the lottery. I'm not inclined to think that it will be me who gets supremely lucky in this case, even though I know that somebody will be very lucky. So bridging the analogy back to an Everettian world, we could think about before however many n trials of an experiment, an unlucky subject S's temporal part at temporal part P0 at time T0 can know that it has unlucky successors, but P0 doesn't know that it will uniquely have any unlucky successor because P0 does not uniquely have a single unlucky successor. P0 has a plurality of successors, most of which are lucky. So if you find yourself instantiating a very unlucky temporal part, you still have reason to be surprised that you, as that temporal part, are quite unlucky. Why? Because you know that your previous temporal parts, your past, essentially, gave rise to mostly epistemically normal, or we could say lucky, entities, and that your temporal part in this one unlucky branch is, surprisingly unlucky, even if we knew that that entity had to exist, given the way that the way functions should evolve according to Schrödinger's equation. So accordingly, it should not come as a surprise that temporal part Pn is surprised to witness, another upward deflection again and again and again. So the second, probably more important allegation by Albert is that Everettian pictures of the world are not going to be susceptible to the ordinary kinds of confirmation and disconfirmation by means of experiments, or at any rate by the ones remotely like the sorts of experiments that we normally take to confirm quantum mechanics. And then another question here is, why should such a result cast any doubt on this theory? So if we see an unlucky string of results, why should we think that this casts doubt on quantum mechanics rather than confirming many worlds, right? Say, well, many worlds said that there would be this very unlucky string of results. Why should we take this evidence to kind of disconfirm quantum mechanics rather than just confirm many worlds? So here's where I try to bring in the thought experiment to at least motivate Albert's worry a little bit. I'm not sure that this one succeeds, but I wanted to go for it anyway. So David Wallace star is a subject partially constituted by temporal part P1 at time 1, which is David Wallace on the 1st of January 2023. Now beginning at some time T2, every experiment that David Wallace performs, for some reason he's going to start performing experiments measuring the z-spin of a particle. Wait, sorry? Change of career, right, yeah. Is going to yield the same result of just z-spin up over and over again. So prior to T1, all of Wallace's observations appeared to conform to the Bohr rule. He's a committed Everettian, thinks that, well, we've heard about all these experimental results, perhaps performed a few ourselves, and everything seemed perfectly good with many worlds and with quantum mechanics in general. But after an appropriate number of trials after T1, the results that Wallace stars temporal parts are observing are going to be those that we would consider to occur in sufficiently low-weight branches, the kinds of branches that we should think disconfirm many worlds, or that at least cause us to maybe want to reject many worlds. So yeah, he's going to be observing results that should motivate him or his future temporal parts to reject many worlds. But on the other hand, Wallace Starr's earlier temporal parts wrote in his 2012 book, yes, that an experimenter should reject these. Sorry, getting a little bit flustered here. Oh, I'm missing a point. Oh. My point, the point that I'm missing here is to specify not only that we have this intuition that we ought reject many worlds given these low-weight outcomes, but that perhaps we also predicted that somebody like temporal part Pn in January 2043, after observing all of these results, had to occur. There had to be a temporal part of the Wallace star worm in the unlucky branch that was very, very, very unlucky way down the line. And there had to be a branch sharing a temporal part with David Wallace in this room that would be profoundly unlucky if you chose to start doing these sorts of experiments. This is a straightforward, I think, consequence of the branching in many worlds. So the first thing to note is that it shouldn't be surprising that maybe after all of these trials, David Wallace wants to now reject many worlds. It's normal for us to change our views over time, and it's normal for us to attribute different beliefs to one temporal part than another one, because yeah, we think that we update our beliefs over time in accordance with new evidence. So that seems pretty straightforward. But what is surprising is that David's temporal part P1 at T1, the one before this zany string of experimental results occurred, knew precisely that he would have these unlucky successors at these later times. So the tension here is between the knowledge that this must occur, that you will have temporal parts that are profoundly unlucky, and that you have a good scientific reason to reject a theory when presented with evidence that seems highly abnormal, and perhaps shift over to some different theory. So the general premise conclusion form argument is this. So we have Wallace's principle: if one detects results associated with low-weight branches, then one is rationally compelled to reject the many worlds interpretation. Premise 2, Wallace Starr's temporal part P1 at T1 knows that some of his successors will be unlucky at the later time Tn. Premise 3, by Tn, Wallace's temporal part Pn has consistently observed results that are associated with low-weight branches. 4, Wallace Starr's temporal part Pn at Tn remembers and knows at Tn that he made these earlier predictions that he would have unlucky successors. He has the memories of his previous temporal parts. And 5, as an Everettian, temporal part P and N at Tn is rationally justified, perhaps, to accept many worlds on the grounds that his earlier temporal parts made this prediction that has now come true. I will have unlucky successors, and now I am instantiated as these unlucky temporal parts. But on the other hand, we're rationally compelled to reject many worlds from premises 1 and 2. So therefore, the temporal part Pn is rationally justified to both accept and rationally compelled to reject many worlds, and so there seems to be this apparent contradiction. Now I think a lot of people here are going to be inclined to not buy this fifth premise. Perhaps most of us think that we're just not rationally justified to accept many worlds on the grounds that you have previous temporal parts that make these predictions, because they're supposed to be very, very unlikely, even though we think you do, in fact, or you must, in fact, have temporal parts that are unlucky. They make up a very small percentage of the overall weight of the wave function, right? And we might think that they can be rationally ignored. Perhaps they're better off being rationally ignored. So that leads us to the first option, which is, given this apparent contradiction, we might just think we should reject many worlds. This is, I think, the option that David himself suggests in his book that abides by this principle that we are rationally required to reject many worlds if we observe low-weight results. And the advantage of this is that it seems like we do have some criteria for disconfirming many worlds. We seem to avoid one aspect of Albert's worry that any experimental results we observe will confirm many worlds in some way. So, on the other hand, endorsing this claim does require that a subject like Wallace Starr rejects the theory that predicted precisely what he would observe. Yes, I will finish up right now. Great. On the other hand, we talked briefly about accepting many worlds. One of the advantages of doing this is just the intuition that as losing my mind here. As was briefly discussed earlier by Tim Maudlin, we don't just think that this is that these unlikely events are unlikely in the sense that they'll probably never actually happen. We think that they actually do have to happen if many worlds is right. So it seems weird to just totally deny the kinds of empirical support that this seems to bring to many worlds. If something supposedly very, very unlikely or very, very low weight occurring was entailed by the theory. So in conclusion remarks here, if we're already familiar with many worlds, we can make sense of the sense of surprise generated by low-weight results in terms of perdurantism and self-locating uncertainty, and I think avoid at least that aspect of Albert's allegations. Then, in the cases like Wallace Starr, it seems at least apparent to me that there's some way to entertain his claim that the atypical results can support rather than disconfirm many worlds, but I do think the motivations to continue accepting many worlds appear fairly weak. And I didn't get around to the middle thing, but we could talk about that later. Thank you. Sorry.
Thanks very much.
There are some technical details with many of which I will agree. But there is a main thing which for me is completely not acceptable, this is the approach. The whole idea, as I understand many words, you cannot know who you will be later. This, if I understand, this is the approach. There is Bohm, I know if I'm a Bohmian, I know I will have one future. If I am Albert Lohr with many minds, there are some special things. But in your case, your worm is kind of philosophical concept and not a real concept. You say that now there are these two worms, and they're absolutely identical. And you say that the super, the one who sees the block universe will call that you are which will go to this one. There is no meaning for this. You have to admit that you add hidden variables, so it's not many words. But the whole idea of many words, psi, period, nothing else. You add some worms. Without adding worms, even the God cannot do what you say. So this is a question. Can we have situation when we can ask, who will I be in the future? I believe there's no meaning for this. I will be all of them. And my solution of this, you say self-location uncertainty, it's not this worm will be. I will be everywhere, but when I'm in every branch, I don't know who am I. It's not, I don't know where am I don't know who am I. This is self-location uncertainty.
Okay, thank you. Yeah, so the way I was defining a person like you was as a worm. So you have a history. If you don't know what your end will be, but you have, you do know your past.
Yes.
Right? You know your
no
past.
problem with past. I can define my past, not the future. The past is well defined. unless we have this Wigner friend, and then I will have double pass to whatever. I don't have loops. But if no Wigner will perform experiment, I have unique path. But future? No way. There is no meaning. No scientific. I'm a physicist. I need some parameter. And there is no, in many words, in wave function, there is no this parameter. Worm is not there. So you cannot, I cannot ask where will I be. I will be everywhere.
Right. So you, as the worm, don't know your future, in my view. I must have miscommunicated that. The idea is that you, instantiated as a temporal part at a particular time, have a plurality of successors. All of them are successors of your temporal part at any given time. But when I say Lev Vaidman, what I mean is Lev Vaidman along one particular branch. No, I don't. Yes, sorry. Oh, sorry, thank you. Yeah, the way that I'm defining an object in the perdurantist terms is going to be this temporally extended thing. But
I cannot talk to the future. You cannot talk now about me in the future as single. In the future, I'm not single if I will use my word splitter or I perform quantum experiment. No way to talk about me in the future. You can talk about me in the past. No way to talk about me in the future, about you two.
okay. Yeah. Yeah, thank you.
Thank you. There's a couple of things it might be worth talking to offline about how to think about the temporal parts thing, because I think there's an issue there. But let me not try that now, because it'll get complicated. I wanted to make a sort of more minimal point. I mean, I think the view that you accept that one might decide to accept the many worlds theory, even in the face of what we normally call disconfirming evidence, and that will be okay, I think sounds okay if one's thinking about something as broad as shall I confirm many worlds, right. But there are more specific versions of that just aren't going to be acceptable in an Everettian framework. So let's suppose after this conference, I'm now totally happy that many worlds theory is true. I'm dogmatically confident in it, and I'll leave philosophy and start measuring spin-half particles. My rationale for doing that is I want a device that produces the perfect spin X particle, and so I'm going to keep measuring my system in the spin Z basis and count the statistics. And after I do that for a few years, I find that every single time my device has produced a particle, I find it has plus spin in the Z direction. So I need to be able to take that as powerfully powerfully falsifying of the claim that this device produces spin X particles. I need to be able to recover just mundane calibration claims about the fact that if I measure a system lots of times and the system is reliably producing states of a certain kind, that I can image what states it produces. If I don't have access to those kind of more mundane Bohr rule situations that apply in state tomography, then I'm just going to struggle to do ordinary physics.
Right. Yeah, I think that's a big worry here, and I think that's one of the major reasons to not side with this intuition that perhaps you do have reason to keep maintaining belief in many worlds, given these weird results. It might be better to assume there's something wrong with your equipment and look for that, or that perhaps the fundamental laws are just very much unlike the way you thought they were, because that's what your experience suggests, right? Yeah, good.
I mean, I guess put it this way, Albert's point, I take it, is that it looks prima facie as if we should regard many worlds as confirmed by any data, and that is epistemically unacceptable. And I think you're exploring the interesting idea that maybe it's not epistemically unacceptable. I guess what I want to say is I think Albert is right that it's epistemically unacceptable, and you can see that just by looking at state tomography outside the broader do I confirm Everett framework. So the Everettian then needs an account of confirmation according to which we're not led to this conclusion because it's epistemically unacceptable.
Oh, great, thank you. Yeah, that's very helpful.
I'm sorry, I think you are both missing an important point. So there are experimental results that cannot be resolved by just a change of quantum state. If you do a Bell test, for example, and you evaluate the Tyrrellson bound, that's it, the theory is over. There is no quantum state or measurement device that can reproduce that result. So you have to reject many words.
Thank you.
Right, yes, thank you. It's just to say that it's a well-known point, but I think it's worth reminding everybody. So let's suppose GRW is correct. We all believe GRW. Hundreds of years go by, thousands of years go by, everything is fine, GRW is fine, but eventually we find anomalous statistics. Probability 1, we will eventually find anomalous statistics. So I don't think that's a problem. But I think it's just a feature of probabilistic theories over long enough times. Now, of course, you can always say, well, we never look at long enough times for that. We're always looking at the short-term view. The improbable thing, it's not that it occurs rarely, it doesn't occur at all. One can always do that, but is an adequate response. The point is, in a GRW universe, inevitably the theory will be disconfirmed eventually, if you take unlucky runs to be disconfirmed.
And do you think that ends up being the case in many worlds as well? Or is
It exactly translates into many worlds, of course, except that it doesn't need infinitely long times. It happens immediately, but across a large number of worlds, very few of them. So it's the usual inversion of a diachronic to a synchronic thing.
Thank you.
Do we have time, or I mean, okay, yeah. Okay, yeah, thank you for the talk. But it's just a reflection, and I'd like maybe to hear you react to it, because I feel like all this seems to be very many worlds, but it seems to me also, it's just a feature of probability in itself. You can think of classical world with infinite space. Okay, so there's infinitely many Hubble bubbles. So there's infinitely many civilizations, and they have all tossed coins since the beginning of their civilizations. And some of them, in fact, infinitely many, will have observed just heads. And they have textbooks saying that when you toss a coin, you see heads. And there's no link with Everett and many worlds. It's the way it is. But I feel like this whole program of trying to rule out these places is sort of motivated by the fact that we should not be allowed to have wrong theories. Whereas we know that the civilizations that have just, tossed coins, and they say every time you toss a coin, it falls on heads, they're wrong, but that's fine.
It aligns with their evidence, right? Like, if they came to the right theory, that would be weird. If they,
yeah, exactly, exactly. So yeah, basically, I'm puzzled about this whole program of trying to make sense of unlucky observers, and why not just accept them, and they're there, and that's fine.
Yeah, good. And I think that's what most people do. I guess one thing that I really should have tried to emphasize more, and I just get very flustered sometimes, is that I think there's a relevant difference between the case of somebody who's permanently unlucky and as such is never able to derive the laws, and maybe somebody who is unlucky, is lucky and observes normal measurements for, let's say, the first 10 years of doing research, and then all of a sudden things go awry. And that seems, it could happen in a classical universe as well. There's no ruling that out. So I'm not convinced that it's unique to many worlds, but it is something that I think is directly entailed by many worlds. And it seems like in that case, where you have very good reason to believe in many worlds before things seem to go awry, perhaps you have some motivation. I can at least see the intuition that somebody might have to say, well, maybe this is a consequence of many worlds, even if it's a very unlucky one, rather than thinking that the fundamental laws of nature have miraculously changed from going from, normally we observe roughly 50-50 probabilities to now the laws say we're going to observe 100% spin up. So that's where I think the intuition is for me and why I keep wanting to dig into it. But I do agree. I'm not convinced that it's different than in the classical case. Okay. Thank you.